Hey everybody, good morning. Buongiorno. My name is Wolfram Hempel. I'm running a small shop with a number of people that is building a real-time data platform. And as part of that, we've developed a feature that's a little bit arcane, a little bit strange, and that caused us an awful lot of headache. We developed a feature that we call real-time queries in the end. We show you a little bit what it is and how we kind of bent Postgres to do this, which was quite easy. And then how we got it to do it at scale, which turned out to be incredibly hard. And I want to talk a little bit about what it is, but I also want to talk a bit about our journey to ending up at Postgres yet again. This talk originally used to be called, oh, it's Postgres again, just to kind of outline this. But I hope you kind of see where we're coming from and how we arrived there. So to give you a little bit of background, we started off as a quite popular open source project called, and where is the thing? There. Called deepstreamIO. Deepstream used to be a tiny real-time server. It did three things effectively. It did what we call data sync, which is a synchronization between persistent objects across clients. And a client here can be literally anything. It can be a backend process written in any number of languages. It can be a browser, a mobile phone, or an IoT device. And on top of that, it also does more classic pubs up and request response. But as we grew this into a platform, we wanted to go a bit beyond. We created this thing, it's called deepstreamHub, and it exposes one feature that I want to talk about today. I'm not sure how well you can see this actually. Probably not particularly. All right, I'll do my very best to describe it. What we wanted to do is we want to have the ability to do real-time queries. So things that are not just retrieving a one-off result, but effectively queries that keep the result set open and stream new entries as they match or unmatch the search criteria. And there's a wide array of use cases for this stuff. This one is one of the most popular ones. Think finance, for instance. You have a bunch of stocks. You want to order them by how well they perform in a given day, like the top 10 risers, top 10 fallers, or something like that. And in its current state, this needs a lot of specialized implementations, and companies like Sangard and others produce dedicated solutions for that. We wanted to create a completely generic way of doing this as a one-stop shop. So code is a little bit hard to read here, but effectively what it does is it retrieves a list of things, and this list is created using a number of criteria. It specifies a collection, Standard & Poor's 500 in this case, and then it specifies a number of JSON-ified parameters. So order by, performance, ascending, limited to 8 results, and the query we're interested in is anything where the industry equals to biotech, just as an example. And the goal, of course, is you get your result set and every change is pushed to a client. Now here's a little bit how we got about this. In our data structure world, there's two fundamental concepts. There is something called a record, which is just a document of relatively schemaless JSON that can be manipulated and observed. And any change to such a record is synchronized across all connected clients within milliseconds. Each record is identified by unique name. So we're talking a little bit like object-oriented database, Mongo-ish ideas here. And these record names, record IDs, can be arranged in lists. Lists are just flat arrays of strings that identify documents in a specific way. Now, in order to implement such a real-time querying system, we wanted to send a list with a magical name composed from search parameters and return a list that happens to have the exact result set based on these, and that's dynamically created on the fly and kept up to date. And so began what we're now calling kind of our search for a right DB. Now, at the time, we started with a project called Rethink Db. Can I quickly ask, who's familiar with that? Rethink Db? Yeah, see, that's exactly, that's the problem. So Rethink Db is actually quite a clever take. On their website, they had this example, and we saw this, and we thought, hold on, this is spot on. This is exactly what we want. How cool is that? And it's been a really, really clever take as well. It's like a hybrid between object-oriented and relational databases, which kind of appeal to us. It's very easy to get started with. It uses its own query language called ReQL, which is inspired by the way that functional query builders work, right? So each argument, rather than passing a long string as in Postgres, is an individual function with its parameters. So you don't have to worry about SQL injection, you don't have to worry about concatenation and the likes. You just run your functions, and behind the scenes, it somehow magically builds up a query, and you don't even know how. So we've been really excited when we found this project, and we were a little bit concerned initially because there weren't any too big adopters, but it was a Silicon Valley startup, right? So how can you go wrong? Some 60 people working on it, huge traction, huge financing by Andreessen Horowitz and whatnot. Very cool, very cool. And the first impression was really positive one. And then we rolled it out into beta, and it started to get a bit dodgy, really. Whenever it came to network partitioning, for instance, a bit of data went missing. Not bad, but enough to spark concerns. And whenever we start our real-time queries, they provide these exact results. It's actually really nice. You see this on top, right? You select a table, you tell it to order by a certain aspect, you specify your limits, and just by virtue of adding this word changes to it, you get your real-time result feed. So really cool initially, but these real-time feeds kept stopping at some point, right? It was all a bit rubbish, really. Now, 3-4 months in using it and thinking we've been a bit stupid, maybe we set it up wrong and so on. Yeah, this happened. And we realized that we weren't the only ones that had these problems. So no, probably we did it wrong, but it also was generally quite broken. All right, fair enough. This was a bit of a shocker. The project still lives. It's now been migrated to, I believe, the OpenStack or OpenOcean, one of the foundations, basically. But it's very much running on low steam. But it's a very cool idea, and if it had worked, it would have been spot on what we needed. All right, we thought, we're running on AWS, all right? So maybe our savior will be one of the AWS databases. And we went for DynamoDB. Can I ask once again, anyone actually using this on a large-scale production project? Exactly. So honestly, this thing is crazy, like literally. For those of you not familiar with it, it's a object-oriented database that feels very, very similar to MongoDB. In the way it works, in the way it's structured, its documents, and so on. And it has one feature, similar to MongoDB again, that makes it quite an interesting fit for the sort of thing that we've been after. It has a change feed, right? It's just a fire hose of all the changes that any client makes to any document. It takes quite a bit of processing power to take this in at scale, but fair enough. There's a real-time change log that you can hook into, you can listen to certain tables, you can partition it a bit, and you can build your solution on it. Now this sounds a bit ambitious, but who's familiar with Firebase? Okay, that looks a bit better already. It doesn't anymore, but at the time this was sold to Google, it was actually architected exactly that way. It was based on MongoDB, it hooked into its change feed. Each one got one document, and the changes were kind of synced automatically on top of that. So this encouraged us, right? This felt, this has been done on scale, and even more so, this has been done on scale at a company that's been acquired by Google and is now a large-scale project. So how bloody bad can this be? Well, to do it short, it's pretty bad. The ones that are familiar with you, this is such a bloody bizarre project. There's so many things you have to do. You have to, for instance, provision how many reads and writes you'll have on the table that you just created for all eternity. Like right at the beginning, when you set this up in development, you have to say, I'm gonna have a maximum of 5 writes a second. I don't bloody know how many writes a second I'll have. And it's priced on that. From the very beginning, you need to commission for what you will ever expect it to be the maximum. And this kind of really killed it for us. The API was clunky. The clustering didn't just work. This is one of the least popular Amazon services, and for a reason. All right, well, this was really the point where we kind of thought, well, we need to cut our losses here. Let's go back to the classics, which is very much why I'm talking at this conference now about the whole approach and how we went about it. And we started rolling out a Postgres cluster to implement these sorts of searches. Now, the first step to doing this was really easy. We took our JSON, contained within the list names, and we generated very basic Postgres queries from it. So this one, very straightforward. We take our JSON order and translate it to Postgres order by. Easy bit. But here's where we get a little bit trickier. From there on, we've taken this Postgres statement, and this is just one example, and put it into a function. So far, so straightforward still. These can become a bit bulky, but nonetheless. And this function is run on a trigger every time anything is modified. Now, let's go back a quick step. Since I kind of know from back, Postgres functions seem to be a kind of rarely used features, but they're really, really powerful one. Effectively, you can register any kind of routine with Postgres up front, and then call it in a myriad of ways, injecting properties and variables into it. You do this by creating it with a unique name within a given Postgres database. You define what kind of parameters this function expects, and you declare, well, it's very similar. You declare return types and so on up front. And in the middle of it, you have your actual function execution, and these can actually be written in a number of ways. We used something called PGSQL, which doesn't exactly roll off the tongue, but it's the procedural language of Postgres structured query language. And I go into details lately. We went through a few iterations on that. We benchmarked a lot, and we want to find out how we get the maximum in speed, performance, but most importantly, parallelization out of that, since this is the really challenging bit. Now, what we do here is we execute the pre-compiled query we have within a given schema and its table. And there's a thing. Oh, ooh, it's green. Very nice. And once we have a result, we execute another statement which triggers a notification. Now, notifications are another really cool feature in Postgres, which effectively turn it into a relatively basic pub/sub messaging system. Rather than keeping a persistent connection open, rather than keeping a short-lived connection to your database, executing your query, getting results, and putting the connection back in the pool, you keep a persistent connection open. You register a listener, and from there on, via your persistent connection, you will receive notifications every single time such a statement is executed. Each notification has a given name and can have any number of arguments. So for our use case, we cast all the IDs of the results we found into a comma-separated string, and we notify the user of them. Now, the only thing that's missing for us really was we needed to register our trigger. We needed to tell Postgres when to run this, mainly whenever anything is inserted, deleted, or updated for a given table within a given schema. And it should do so for every statement, as opposed to every individual row, and run this method. And as soon as the client indicates they're no longer interested in the result set, we simply deregister this trigger, and this is actually missing here, we also throw away the function, since the function is bound to this specific query, so there's little reusability around this. Cool. All right, so this was encouraging. This worked actually pretty well. And then the trouble began. Because, does it scale? Kinda. Let's look at the implementation problems, really. First of all, we have the the classic challenge. We have a power law in there. We run our function on every operation, on every row. This is really expensive. It's operations times rows times searches. And this is the sort of thing that really, really gets your database to the knees. So how did we go about optimizing this? Well, first of all, we spent some time experimenting with how we actually register this trigger when it's being run. Looking at the statement, you have a bunch of choices. You can tell it to run the trigger for each statement, or you can tell it to run the trigger for each row. Now, for each row, of course, is a really cool thing to do in certain use cases when you actually want to execute something directly after a row is added or manipulated, and potentially even alter the table itself. But we didn't want that, right? We have a simple search, don't do any, it's a fairly immutable thing, we don't do any edits to the table underneath, and as a result, for each statement was good enough for us. And already, this kind of takes one order of multiplication out of it, to an extent at least, since the query itself still has to iterate through all the rows within the table. Next up, we found that we can run our queries before or after. This one's tricky. If you actually trigger your function before the edits, it's significantly quicker. Why? Well, Postgres has to actually schedule the execution of your function, and for that it will load it into memory rather than on disk. And it will have to queue it up in there. And depending on the complexity of the operation at hand, this function will be queued for a considerable amount of time until all the updates are run. Whereas if you run it before, it will be executed, dropped from memory, and memory will be freed up. This doesn't seem significant as a one-off thing, but it is when you do this again and again across hundreds of thousands of parallel queries. We didn't really have a choice here. We needed to search within the altered result set, so after this. And we did actually find, it didn't make sense, but when we ran a test, we could improve performance 3 to 4 times by simply moving the trigger before. All right. But most importantly, we're running on Postgres 9.2 still. Postgres 10 is out, of course, and it has the one saving grace that we really would have needed back then. It has one additional declaration you can have within your trigger creation, which is this line. Now, as of Postgres 10, you can reference virtual tables containing only the changes that were made for the given operation, and only search through these rather than through the whole table again and again. This takes one whole order of multiplication out of our problem initially. And this is brilliant. We haven't deployed this yet. We're still in the process of benchmarking it, but it literally speeds the thing up 10, 12-fold, depending on the size of the table it needs to go through. And it's a really, really brilliant feature, actually, that we're looking to improve intensely. Now, the next thing that we looked into is, what do we do about the search functions themselves? Now, first of all, which language do we write them in? Postgres supports a number of languages. You can write them in plain SQL, in its procedural language, in low-level C, and you can also have bindings into a number of other programming languages. We started by writing ours in C, which is of arguable enjoyability, but that's a different problem. We started writing ours in C, and then felt, well, this is getting quite complex now, and we're largely responsible for memory management and the likes. Postgres does its very best to sandbox these executions, but global variable declaration and the like still need to be cleaned up yourself. So we did some benchmarking on that, and we found that really, at least for our use case, there's little to no difference in terms of performance. Using Postgres procedural language, in fact, performs pretty much 98%, I think 98.4% on par with a native C execution. So super happy about this one, and we switched to PGSQL. Next up, we looked at the nature of our function. Postgres lets you declare 3 types of functions. You can say, my function is immutable, not even given the same input, but generally it will always perform the same action, produce the same result. or it's stable, meaning that given the same input on the same table, it will always produce the same result. Or it's volatile, meaning God knows what kind of result it will produce. By default, all the functions are volatile. And this is something we've overlooked initially. So this means that Postgres has a hard time scheduling your function in the most efficient manner and optimizing it up front. By virtue of, now for us, our function didn't manipulate the table in any way. It didn't interact with the data, right? It's just searches. So this is like a classic case of a stable function. Look at a table, get the same input, get the same output. This improved it by 3 to 4 times in performance, really. This made a huge, huge difference when it came to scheduling and parallelization. And speaking about parallelization, actually, let me skip forward quickly. This is another thing that really kicked it off. You can tell Postgres up front, do you need to run these functions in sequence, or can you parallelize them? And again, the default is the unperformant case. The default is these functions are run in sequence since, who knows, they might be manipulating some data and then reading it again, and their changes might be based on the manipulated data. So let's play it safe and do it in series. Once we switch to parallel mode by telling it, hey, this is parallel safe, of course we could run it across threads and performance skipped quite a bit. And likewise, we declared our function to be leak-proof. Now, this is kind of weird, but imagine your function, say, throws an error or has any side effect beyond its return value. By saying it's leak-proof, you say, well, this is not going to happen. We know this for a fact it's not going to happen. Don't account for that. And optimization kicks in, and again, it speeds it up by quite a bit. And finally, we looked into our deployment. Now, we're running many separate distinct clusters of Postgres nodes fronted by a single write instance that then replicates to 20 and more read instances, read replicas. They're purely read, and this is where our searches are run. And the interesting thing here is, I mean, Postgres has amazing clusterability, of course. However, we found that we reach a performance peak around 2022 read replicas. If we added more, the process of actually syncing and making sure all of these stay in sync led to a performance decline as opposed to improvement by more parallelization. If we added less, we're missing out on potential computing power. So again, for us, around 2022 seemed to be a magic number. It took us a while to get there. And each of these read replicas can run around 1,200 of these searches in parallel at a time. And from here on, it's just a multiplication exercise, right? More clusters times more read replicas times more searches leads to a very decent amount of parallelization. Still, though, this real-time querying, as we found, is by no means a cheap operation. And it's one of the core drivers behind hardware and infrastructure costs for us right now. Going beyond, though, there's some other limitations as well. Now, first of all, by the very nature of this setup, you have to work with a single table only. You can try to parallelize things. You can try to register multiple triggers, the same trigger for multiple tables and the likes. But this is where things really got complicated. Because due to the nature of injection values and so on, we started seeing a number of race conditions in our implementation, really. And so we limited down to one table, and this seems to work well. But most importantly, the only point where we can run these is when actual change happens. So if you look at these two queries, in quotes here, assuming you're running a CPU monitoring tool, you get these sorts of values, you get your CPU utilization and the timestamp when this has last been updated. First query, give me a real-time view of all CPU nodes above 80%, since who knows, I want to trigger alarms on them, or I want to put them on a warning list or so. Perfectly fine, right? On every every write I can check, has it exceeded 80%? Golden. this is something that our users try to do immediately, saying, all right, cool, so this is great, I can measure CPU, but I also want to know if a node is dead or unresponsive. So let me just look for a timestamp that's less than 100, less than 1,000 than the current one, and update me on that. But that, of course, doesn't work for us, since we're running a trigger-based architecture that only executes their queries on a change. So saying, hey, less than 10 seconds, if a change happens, this will trigger. But if no write happens, which is exactly what you want to look out for, it doesn't. We have yet to find a good way to work around this. This is one of the strong limitations right now, and is putting hard limits on the infrastructure, really, and the usability. And I do apologize. I think this might have been a bit too quick, but final question, did any of this make any sense? And did anyone have similar experiences or has experimented with that feature set and can share that? Thanks so much.
Did you consider any Windows function as a possible solution?
This is a really good question.
Custom Windows function.
It's a really, really good question, yes, actually. I think the key to solving this at scale is still in creator segmentation. Having said that, the inclusion of the ability to only search through a virtual table with the changes in it is kind of that already, in a way. So we were looking to implement this ourselves. Thankfully, it came out in Postgres 10 now. But I genuinely believe breaking this down in more and more parts is exactly the way to go. Look into stream processing approaches around that as well, basically, where for a larger table especially, you break the table down into multiple subsegments and process each individually and then aggregate the result again in a MapReduce fashion, is as well how you go about that scale. So far, we're trying to mitigate this by breaking the data down upfront into multiple tables and then keeping the individual table sizes comparative low, like a few million rows. But I think beyond that, this is the way to go. It's a really good point.
Another question?
I never tried this out, but you were talking about parallel save clause, and I understood that Postgres was process-based, so it's gonna fork more processes, more threads.
So this is where I'm not super sure, since I assumed you can actually set it, but people in this room is way better than I am. It does parallelize queries already, but it runs things within a certain sequence that you want to enforce. We are running, and again, I'm not the infrastructure guy behind this, so I'm a little bit shaky, and please forgive me if I'm wrong here. But we're running multiple processes in parallel by default, as opposed to spinning it up on demand. And it's now being distributed across them. This is what we saw. I'd love to provide a better answer, but I'm not super sure.
Other questions?
I don't know if I have understood everything, but how do you handle concurrent inserts into the table? Because concurrent inserts will create multiple times the trigger firing. And in this way, you will have some debouncing problem. You have too many triggers firing and notifying concurrently. So you should have a way to debounce all these concurrent notifications.
It's absolutely true. We've been lazy. We're not doing this on a Postgres level, actually. We're accepting every incoming notify message and debounce this on the application level before we send it out to the end client, actually. It's exactly true. Seeing that we run it after statements as opposed to after each row, there's already a little bit of aggregation. But especially about use case like finance and so on, you can easily get 100, 200 notifications a second, and there's no point sending this out. So we're doing exactly that. We're receiving these notifications, we're running the queries, which is inefficient, but then we're bouncing it before we send it on. It would be cool to move this to a Postgres level, though, since it's unnecessary traffic on the wire.
Maybe I missed it, but what kind of amount of data are we talking about, and what is the infrastructure running Postgres? Just to have some raw numbers.
No, so this is an excellent question generally. So we're currently looking at about 10, 20,000. It's still in beta, but we granted access for around 10,000 active users who run about, at the moment, 20, 30,000 of these queries. The amount of rows is relatively high. So we're talking about 10, 12 million rows per user that each query has to run through. But the data within these rows is very, very small. It is, however, binary JSON. So it's also JSON search, which works, but it's not what Postgres likes the most. The throughput here really is, this runs on 2 clusters of 21 nodes each, one write and 20 read replicas, and we're running it on AWS, but we're running it ourselves. So not using their relational database services or Aurora or anything, because there's a lot of fiddling with the actual Postgres setting going on. We're actually running it on T2 medium machines, which is not the most ideal one, but the one that provides just about enough performance for the money you pay. Bigger ones would be nicer. But right now, this seems to be like a kind of good compromise. And one Postgres instance per machine and nothing else.
Any other question? Okay, I think that's it. Thank you very much, Wolfram.
Thanks so much, guys.